Okay, let me take the camera on. Okay. Okay. So right now internet bandwidth is okay. So I believe there is no problem. Okay. So okay. So if my screen is visible, so today we'll be talking about basically how nanoelectronic systems, or let's say different nanoscale systems, can be characterized through transport measurements. And so the idea is the following. So that like there are different nanomaterials, or let's say nanoscale devices we do work with on a, let's say, day-to-day basis, or let's say in research labs, I mean, or in the industry. Now, most common type of characterization which can be useful at a lab scale is doing some sort of transport, or let's say electrical characterization, to be kind of more simple or in a basic term. So the idea is to focus on that particular direction. Of course, this is not the only way to characterize these systems, but this is a very useful way. And it can start with very simple concepts, and it can be more and more, let's say, elaborative, and like the things can be done up to, let's say, at a very exhaustive level in order to measure very small signals. So the plan is the following. So I'll first start with a basic introduction of nano electronic systems, and then I will basically kind of like describe what is a nano, I mean, kind of like a nano electronic device or system looks like. Then I'll talk about basic electronic characterizations, and how do they kind of be used for measuring different nanoelectronic systems. Okay, so let's start with this. So first of all, whenever we are talking about electrical characterization of devices, then we mostly deal with silicon-based systems. That means the chips or devices are made up with silicon. Now, silicon is something. Okay, just give me 1 second. I'm getting a phone call. Okay, just give me 1 second. Just give me 1 second.
Sure, sir.
Uh, Sorry for the inconveniences. Okay. Okay, so now when we are talking about, let's say, an electronic device, then mostly they are some field effect transistor or some sort of similar type of devices. And in our day-to-day life, we do use many of those systems. Let's say we use like smartphones and laptops and computers, etc. And if we go and open up any of these systems, then we can get to see like some sort of structure like this, which is basically, let's say, having some motherboard, and which will have basically multiple components, that is mostly transistors or integrated circuits which are fitted inside it. Okay. Now, usually there are billions of transistors which are inserted into this small tiny chip. Now, in order to have kind of a large computational power, or let's say fast processing, we do need that many transistors. And in a way, this is an, let's say, big development in this direction, that the chip sizes have been reduced up to this particular level. Now, if we look at like how does this technology has evolved with time, so we can look at this graph. So on the y-axis we have number of transistors, and on the x-axis we have the timeline, that is the number of years. Now, very simply, if we look at on the trend, then we can see that the number of transistors which used to fit inside one particular chip, that has been manifold in the present time. For example, in 1970, something like few thousand transistors used to fit inside one chip. But nowadays, there are basically, let's say, 50 billion transistors are kind of doing the same thing. However, if we look at the size of the chip, that has gone down. So eventually what has happened is that the number of transistors has gone up, but the total volume in which the transistors are fitting, that has gone down. So effectively, the size of the transistor has gone down extensively. And this is basically what has been predicted by Professor Gordon Moore, who is also the co-founder of Intel. So he has said that the density of this transistor, or let's say the number of transistors on a microchip, is going to be doubled every 2 years. And we have seen that like that has happened over past 50 years. And as a result of that, something very interesting has happened. So if we look at this graph here on the basically bottom inset, then we can see actually that yeah, that here on the y-axis you have feature size, and on the x-axis we have basically year. And so feature size can be something like, let's say, the gate length or the typical dimension of a transistor. Okay, so if we look at this, then we see that that feature size is going down with time, and sometime in the middle of 2000, that number has basically gone below 100 nanometer. So something special has happened at this length scale. So what is this? This is because, I mean, the special thing is that here the let's say as soon as the dimension goes below this 100 nanometer, the system starts behaving in a different way. Why? Because until let's say above 100 nanometer, the classical laws of physics, they govern basically the operation of the transistors, like the way current will flow, or let's say the carriers will move, etc. But whenever we are going below this 100 nanometer length scale, then it is quantum mechanical laws which starts dictating how the carriers will flow or what sort of current will flow at a particular voltage, etc. Now, this has basically two-way effects. So one is that since quantum mechanical laws determine the current and voltage behavior, so classical laws cannot predict that what will be the let's say kind of structure and what is it going to give. Now, as a result, there are quite a few issues which has come up. For example, like sometimes the transistors not switch properly, or sometimes the design has been modified. But other than that, something interesting has happened, that there are new transistor geometries which has come up, and that has opened up new possibilities of different kind of operations. Okay, I'll show you one example. Now, eventually what is happening is that since we are going down in this feature size, so we are almost hitting the end of this line. For example, here you can see this is at 10 nanometer. Now we currently at kind of like making, I mean, the companies are making transistors which are typically 6 to 8 nanometer size. Now, in terms of atomic dimensions, that will typically be like few tens of atoms, like 10 to 20, 30, 50 atoms. Okay, so we cannot go down and scale these transistors indefinitely. So we have to think of some alternative technology, and that is the area of nanotechnology, where basically the nanometer scale dimensions, or let's say systems, will be made at that length scale, and that will give us new types of behavior, and which we will see subsequently in the coming slides. Okay, so now let us take an example of such a nano electronic device. So here one such device is called a single electron transistor. So what is it? So we all know about like field effect transistor. So this is like a source electrode, and we have a drain electrode, and we have a gate electrode, right? So this is something which we all have studied in our, let's say, undergraduate days. And we have a channel which connects basically this source and drain. Now, if we apply some voltage between source and drain and gate voltage, then we can get this IV behavior, and from there we can use it as a, let's say, switch, or other types of operations, for example, design of amplifier, etc. Now, if we reduce the size of the structure, and then we can create something called as a single electron transistor device. And what is it? So here also we have source, drain, and gate electrode, but the channel region is not that big. Rather, it is a very small island, and this is separated from the source and drain electrode. Now, what happens here, that since the island is separated from source and drain, so if I want to have a conduction from source, then it has to somehow cross this barrier, and that happens through quantum mechanical tunneling. So if the electron which is staying at the source have enough energy that is higher than the barrier height, then that electron will travel from source to the island. Now, in the island, if it wants to move from there to the drain, then again it has to have sufficient energy to basically overcome the barrier between island and drain. Now, once that entire process gets completed, then I will get one electron equivalent of current. So here, if I look at the ID VG graph, then you can see that I get a current peak once this electron travels from source to drain. Now, once that is done, then I get no current for certain voltage range, because then next electron has to come and then travel. So once the next electron comes, then I get another current peak, and subsequently, if the third and fourth electron comes up, then I'll get another subsequent current peaks. So here you can see in the bottom figure, which I explained at the beginning, that I get a large amount of current and it is continuous. But here this current is discrete and it is only appearing because of few electrons which are flowing. So that is the difference between the, let's say, classical microelectronics and nanoelectronics. That here the quantum mechanical ways of transport, it determines how the current and voltage will behave here. Now, it has quite a lot of advantages. I mean, this single electron transistor. So, for example, if I know that how many electrons are traveling here, then what I can do is that I can basically control the number of electrons, and I can very accurately control the current flow, and that way basically I can do very low power operation. Okay, so this has quite a lot of applications in metrology, then sensing, and basically other areas also. Okay, so here actually you can see how does the transport work. Basically here, let's say this is the quantum dot or the island. Here there are different electrons, and the energy level can be tuned by this gate voltage. And by way of doing this, one can basically either raise or lower this energy level, and through that method basically the carriers can travel from one side to the other, and that way we'll get the conduction. Okay, so this is one example of a nanoelectronic device. Now, let's say there are such very fancy devices. Now, if we want to measure something at the lab scale, then what we will do? So we'll go to the basics, that we'll see how electrical characterization works. So we'll start here. Let's say, what are the most common electronic or devices that we see in our lab? So here you can see that we have basically PN junction diode, then we have light emitting diode, then we have different types of transistors like bipolar junction transistors, then we have field effect transistors, etc. Now these are something which we see in undergraduate labs, and the way we do measure them, either we have these components, or sometimes in the labs we do have some sort of like a compact structure like this, where all these components have been fit up in a circuit, and then you just have to switch it on. Anyway, whatever be the case, if I want to know how do this particular device behave, then I have to measure the current versus voltage curve, or let's say the dependence between these two variables. Okay, so if I do the measurement, I get certain types of trend, and from there I can say whether it is ohmic or rectifying, or let's say if it is giving us some other kind of effect, etc. Now, the most simplest type of measurement what you can do, let's say if I want to measure IV of a diode, then what I have to do is that I need a DC voltage source, then I connect it in series with a resistor, and then I can measure the current and of course the voltage, and that will give me the IV curve. Okay, now here the interesting part is that the current flows from one end to the other, and this is a direct current. Okay, now here there are two concepts which are very useful. One is current source and other is a voltage source. So here, for example, I need a voltage source. So let us see what is current and voltage sources. So for some measurements we need current sources. For some measurement we need voltage sources. So ideal current sources are something which can deliver a current and that stays almost constant, independent of whatever voltage I'm drawing across those two terminals. Okay, so it means that this resistance, the output resistance, have to be infinite, or basically there is no current that is flowing, or there is no basically short circuit as such. Okay, however, in reality that does not happen. So there is some kind of like resistor which you can think of staying in parallel. So the current which it delivers, it will kind of let's say if the load increases, it decays down slightly. On the contrary, if we look at a voltage source, then here what happens is that we do expect that an ideal voltage source should deliver a voltage which is independent of the current which is drawn from it. Okay. Now, that of course does not happen, because that means that there is no internal impedance which is attached to this voltage source. But in reality, the practical sources do have some internal resistances. So here the voltage, it kind of decays down slightly if I increase the more and more current. So whatever be the case, we these days we have quite a lot of few, I mean, stable current and voltage sources, and that do perform very nicely. Now, if I want to do measurement of a particular device, then before I do the measurement, I need to have some idea about the material property. For example, whether the material is a metal or it's a semiconductor or it's an insulator. The reason is the following, that depending on the nature of the material, the resistivity will also change. And based on that, I need to apply proper voltages and current, or let's say vice versa, I need to measure those things also. So my meters have to be compatible to that. Okay, so now here actually you can see the this is a graph kind of which is plotted as a function of resistivity. So here if I think of metals, then the typical resistivity, it comes up of the order of, let's say, 10 to the power minus 10 ohm centimeter. So this is quite small. Okay, now if we are thinking of superconductors, then we know that they have absolutely almost negligible resistivity. However, if we are looking at a semiconducting material, for example, silicon, then this has a resistivity of 10 to the power 4 ohm centimeter at room temperature. And if we look at some of the insulating materials, for example, like Teflon, then that has a resistivity like 10 to the power 18 ohm centimeter. And if we look at diamond, that is also of similar order of magnitude, which is 10 to the power 16 ohm centimeter. Now, if I look at the spectrum from left to right, then what I see is that there is a order of magnitude change, which is, let's say, 10 to the power 30 order of magnitude change from one end to the other. So you can imagine that if I want to measure the resistance or resistivity accurately of these materials with a single instrument, then that is not possible. So I need to have different measurement methods or protocols to measure these different materials. So let us now look at how can we do these things. So the most common type of way of measuring these things, that suppose I have a sample, and if I know the length and the cross-sectional area, then I can use Ohm's law to find out what will be the resistance of that particular sample. And if I know the value of resistance, then I can calculate the resistivity. And from the resistivity, I can get the value of conductivity. Okay, so what I have to do is that if I have these values, then I can of course subsequently calculate other quantities like mobility and then current density, etc. Now, if I want to do the measurement, then commonly what is done is that we do connect it to a source voltage and then we measure the current. So that is the most common method. Now, whether this method is good or bad, that we'll look at. So most commonly, we'll say that this is not a very good way of measuring resistivity. Why? Because here, if we look at that, the current is flowing at this point or entering at this point, and then there is something which we are not considering at all, that is the contact resistance. So suppose these are metallic leads and we do not know what is the resistance of this material. Okay, so there could be a big difference of the resistivity between the contact and or let's say this wire and the material itself. So there is a conductivity jump there or resistivity difference there. So that can give us quite a lot of error here. Okay, now for some materials, they do work okay, but for some other materials, they give very much wrong result. So unless we know what is the type of sample we have, we cannot predict the resistivity using this technique very accurately. So what we have to do is that first we can look at individual contacts. So let's say we study one contact at a time. Okay. So here, for example, you can look at, this is a graph which has been plotted. So this is actually, okay, I do not know actually how to. Okay, so here, for example, you can see this is a current versus voltage graph which has been plotted basically for an aluminum and diamond contact. Okay, so here there is basically two directions in which this measurement was done. For example, one is in the positive bias range and other is the negative bias range. Okay, so here you can see that it's written that there is a rectifying graph, that is curve A, which is the green color, and there is a ohmic curve, that is curve B, which has been plotted. Now, what is the difference between these two? So curve A has been measured under, let's say, certain normal atmospheric condition, and curve B has been measured for the same device or same structure, but in between it has been annealed, or let's say it has been slightly heated up. I mean, the contacts have been slightly heated up at a high temperature, and then it's cooled down, and then it remeasured. So if I look at this line, that is the green curve, then I can see that here, if I am in the forward bias regime, then the current and voltage behavior is slightly nonlinear. So here I can say that like current is increasing with voltage. Okay. However, if I'm in the reverse bias regime, then it does not change. So the current stays almost constant. So it means that on one side, I have basically a kind of let's say ohmic contact, not ohmic contact, but let's say some sort of ohmic contact, and other way it is rectifying behavior that it is showing. But that is not good. It means that if my current tries to flow from left to right or right to left, then the behavior is different. That is totally not acceptable in a device. Okay. But if I look at this curve B, then I can see that these forward and reverse bias behavior are almost symmetric or identical. So here it means that whether the current is flowing from left to right or right to left, that is kind of giving me same type of behavior. So now I hope you understood that what is the effect of contact. So very simply what I was trying to make is that, let's say from here to here, if I'm passing the current, that gives me one type of behavior, and from here to here in this direction, if I'm doing it, then it gives me something else. Okay, so that's something which I do not want. So now that is the effect of contact or contact resistance, that whether the contact is allowing me to passing current smoothly, that is very important. Okay, now in a two probe geometry, that does not happen. Okay, now here basically the reason why in this particular case this annealing changes the behavior is that above this 1000 Kelvin temperature, when it is heated up, then there is some ohmic contact which forms at the interface, and as a result, the barrier, or let's say the kind of let's say some sort of resistance that it is facing from one side to the other, that stays almost similar on the both ways. Okay. Now there could be different types of barrier which can form at the interface. So let us look at these things. So one of the most common type of barrier which forms at a metal and a non-metal contact is Schottky barrier. And the contacts which we make there is called a Schottky contact. So what is this? So if we look at this graph here, on the left hand side, I have a metal, and then on the right hand side, I have a semiconductor. Now here you can see that metal has a Fermi level, but the semiconductor has a gap around the Fermi level, right? So here the conduction band and valence band is here. So valence band is filled up to the maximum, but conduction band is empty. Now, so there is no direct conduction that is happening here. So if I just make a contact between these two, then you can see that there is no contact, conduction that is happening. But if I leave it like this for some time, then under equilibrium, there will be some sort of, let's say, barrier lowering or induced barrier which will form, or let's say charge accumulation will happen at the interface, and that will give me the height of barrier which is present at the interface in the equilibrium condition. Okay. So now typically here actually is a famous quote by Professor Wolfgang Pauli. He said that God made the bulk, but the surface was invented by the devil. So what do you mean is that that usually whenever we are making a contact, that contact is made at the surface, and the surface properties are usually different from the bulk property. Okay, so now we have something like a depletion layer at the interface. And if I look at this depletion layer can be, or the height of this layer can be different for electron and hole. For example, Here between a metal and semiconductor, this top part is the barrier height for electrons, and the bottom one is for the holes. Okay, so you can imagine now whether the material on the right hand side is a p-type material or n-type material. That will determine whether it will face this barrier or that barrier. Now here, if let's say electrons are the majority, then we say that Schottky barrier height is phi. And so here basically, if there is a barrier, then the current will or current voltage dependence will show a rectifying kind of behavior, which means that only one half of an AC signal will flow and other half will be completely blocked. So that actually happens in the case of a PN junction, what we have seen earlier. So here, if you look at, suppose this is an AC signal, and if I have a, like if I pass it across such a PN junction, then only one half will be able to flow and other half will be chopped off. Okay, so that is kind of, let's say, making it slightly DC type of nature. Okay, so now then what is the solution to this problem? That contact resistance is coming up and that is not giving me the correct result. So what is the solution? So if I want to measure the resistivity accurately, then I can use something called as a 4-point probe. So what is this? So here, instead of a voltage source, I am using a current source, and I am forcing the current to flow across this sample, and I am measuring the voltage instead of the current. Okay, so here basically, if I put the contact at 2 points in the sample, then I can measure the voltage, and from the voltage I can actually get the value of resistivity. Now that method is quite good, but if I do it in this particular manner, let's say if I apply the current on the sample and if I measure the voltage from these 2 points, then that will again give me an error. Okay, why? Because here you can see that if I'm applying the current here, that means the current will only flow between these 2 points. So this part and that part of the sample will be completely kind of detached, or let's say they will not contribute towards the conduction. So now if I measure the voltage between this point and this point, then that means it is basically measuring something which is not part of the actual excitation that I'm giving to the sample. Okay, so here what I have to do is that I have to make this kind of arrangement that current has to flow over the 2 ends and the voltage have to be measured on an area or length scale that is within that particular size. Okay, so that way basically I do not have the problem of contact resistance. Why? Because here whatever error is coming from this side will be cancelled by this side. Or alternatively, what I can do is that I can source this current once in this direction and once in the other direction. And then if I take the average, then that will nullify whatever is the effect of barrier that is coming. Okay. So here you can see basically I just switch the polarity of the current. Now this is a DC measurement. Now alternatively, I can do the measurement through an AC technique. So the most popular and easy method of this measurement is using lock-in amplifiers. So what is it? So typically in a lock-in amplifier, what we have is that we have an AC current source. That means this current source is having a particular frequency. Okay, so typically this frequency will be few 100 hertz. And then we do apply this particular AC signal across a sample. Now, as you know, that AC source means that it will change the polarity. So we now there is some advantage of this lock-in technique, that in a DC technique, what happens is that there could be other frequencies or noises that can contribute, right? For example, let's say our electrical noises can contribute. But here, what happens is that there is a reference signal which is measured. For example, let's say I apply this AC current source across this sample, and then I'm measuring the voltage. So that will also be an AC voltage, right? So now what the lock-in will do is that it will check whether the voltage is at the same frequency or it's at a harmonic of the frequency that the current has been applied to. Okay, so here the detection is only happening at that particular frequency. So here it is only measuring the contribution that is coming up at the source frequency. So that locks the contribution at that particular frequency, which means that whatever frequency other than that is contributing, that will be completely ignored. So that means that we are only measuring the actual sample part. Okay, so that's how this logging things works. So here is actually one small cartoon. Here you can see that suppose this is the input signal, that is xt is a sine a cosine omega t, and there is a reference signal at the same frequency, that is b cosine omega t. Now what lock-in will do is that, let's say if I make an product of these two, then I will get basically, let's say one. So let's say these two frequencies are different. Okay, then I'll get a sum and a difference between these two frequencies. Now, let's say if they're at the same frequency, then what it will do is that it will kind of, after measurement, it will take the output and then it will pass it through a low pass filter. So what the low pass filter will do is that it will block any frequency that is other than that frequency which is desired, and that will give me that particular desired output. And so that way, basically, we can get rid of the noises and other frequencies. Okay. So that is also another method of measuring these things accurately. Now, here, basically, okay. So these are basically different ways of measuring the current and voltage in systems. Now, there is another type of measurement which is quite useful to know the material property. So that is through Hall effect. So what is Hall effect? It is that basically we apply a magnetic field perpendicular to the plane of a sample, and then we do the transport measurement. That means we, let's say, apply a current and then we measure the voltage. But now this voltage is not measured along the path of the current, but rather perpendicular to the path of the current. So here what happens is that, let's say this is a semiconducting material. So now if I'm applying a magnetic field, then there will be Lorentz force which will be kind of experienced by the electrons. Right. So this is V cross B. So let's say if the electrons are moving along this direction, so V and B will be perpendicular to this. So V cross B, that is the force which will be acting in this direction, right? So there will be a charge separation because electrons and holes will be kind of experiencing the force in the different direction. Okay. So if that happens, that means there will be a charge separation between the two ends. And if I measure the voltage, then I will get a voltage difference if there is a charge separation that is happening. And from the sign of the voltage, I can say whether it is, let's say, an electron majority type or a hole majority type of material. On the other hand, I can also talk about the carrier concentration. Okay, so that is another useful transport measurement which can help me to identify the different semiconducting materials and the carrier types and concentration, etc. Okay. So now here actually this is a nice cartoon which actually shows you that thing that we apply the magnetic field, so the Lorentz force is kind of experienced and the voltage is generated because of this charge separation. So the Hall voltage will be basically proportional to the magnetic field. So higher will be the value of magnetic field, basically higher will be the voltage that we measure, and we can measure the Hall coefficient. So that sign will tell me what is the type of majority carrier in this particular material. Now, so this kind of geometry you probably have come across in the undergraduate lab. Now, these days, what people do is that they slightly modify this particular measurement setup. So what is done is that instead of only one electrode, here there are multiple electrodes which are put here. For example, let's say this is 1 and 5. These are the two ends. And there are another 6 electrodes which are put side by side across the channel area. So that is called as a Hall bar geometry. So typically if it's a thin film kind of sample, then one can do lithography or patterning, and then you can make these kind of contact pads. Now here what happens is that if I apply a current or try to pass a current between 1 and 5, then I have option of measuring the voltage between different contacts. For example, I can measure it between 3 and 7, like what I said earlier, or I can measure it between 3 and 6, or I can measure it between 4 and 8. So here basically there is diagonal component and off diagonal components I can measure. Now, why is it important? It is important because there are certain materials, specifically nanomaterials, which do show some interesting property. Let's say like a quantum Hall effect, and they are basically the this perpendicular voltage of the resistivity, it gets quantized. Okay, so in order to explore those effects, and these effects have certain applications also, we need to have this kind of geometry, and that is like needs like nanoscale device fabrication. So here if you want to make a contact on these kinds of samples, then what you have to do is that you have to make use of something called as an wire bonder. So what it does is that, so I'll kind of show the use of these things at a later stage. So very simply, suppose you have made some sort of a geometry, like a Hilbert geometry like this. Okay, and then you want to make a contact. For example, this is my sample. Now, if I want to do a measurement, then I have to connect this contact to the equipment, right? So, of course, I mean, the way it is shown here, it does not work like that in reality, that you don't just bring up a wire and put it somewhere like this. This doesn't work. It has to be contacted properly. So, if you want to do that, then you can use something like a wire bonder. So basically, this is like an entire roll of aluminum wire is placed inside this, and this is like a stitching needle. Now, this is an optical microscope. So what you do is that you, let's say, some sort of like your device is put here, I mean, kept here, and then you bring this thing here, and then you can visualize it at a large magnified version of this thing from this point. And then what you do is that you just, once you are kind of at the proper location, then what you do is that you just drop this kind of, so here is like a mouse, so you can actually use this thing. So it's like a tapping thing. So you tap it, and then this needle will go and it will kind of make a contact. So that is kind of, it's like a stitching, you can simply think of that. One end of an wire will be stitched there. Now you move it. So again, by moving this mouse kind of thing, you can move this stage, and that is kind of, let's say, suppose I made the first contact here, then I move it slightly. So now my needle is here. So now I'll make the second contact, and I can simply, so once the second contact is done, then it is automatically breaking the wire. So here the contact is basically made between these two. So this is something which is done on very small size, let's say micrometer size contacts. Okay. So I hope this part is clear to you. Okay, so now so far we have talked about, let's say, how can you measure resistivity accurately through DC and AC techniques, and how can you make some other useful information, that is Hilbert kind of geometry we can use. Now there is so far what we have assumed is that the sample has a regular shape. So what does this mean is that means sample is quite symmetric, and both the contacts are kind of identical to each other, etc., etc. However, in reality, it can be the case that two contacts or two surfaces are not exactly identical. So they can be different from each other, or the shape of the sample itself could be slightly irregular. What will you do? So the assumption which you have taken earlier, let's say R equal to rho times L over A, that needs the sample to be of some regular shape, right? Now imagine if the area is changing across the thickness, then I cannot use A, right? I mean, the area could be A1, A2, A3, etc. different points, right? So that particular method breaks down. So for any arbitrary shaped sample, what I can do is that I can make use of another technique that is called as Van der Pau method. So what is it? So this is something which has been proposed by the scientist Van der Pau, and this can actually measure the resistivity and Hall coefficient of any arbitrary shaped sample. So suppose if I imagine that my sample is of the shape of a circular disc. Now it does not necessarily mean that it has to be exactly circular. It could be ellipsoid, it could be slightly off-shaped. Now here I mean, under this method, I have to have 4 contacts that have been put like this. So A, B, C, D. So you put it on any particular area. It does not necessarily mean that A, B, C, D have to be kind of like the distance between A and B have to be same, B and C have to be same. It is not that. You put it any 4 corners. Okay. Just 4 contacts have to be there, and no 2 contacts should be kind of falling on top of each other. And another assumption is that the thickness is uniform. That is kind of assumed. But if it is slightly off, then also it works. Okay, so the reason is the following, that here this is like a thin sheet. Okay, so if the thickness is not like varying that much, then this assumption will work well. Okay, so I will not talk very much details of this technique because it will be like an entire lecture. So there are some nice papers actually. If you're interested, you can read this thing. So this is like a entire the proper derivations have been done, and they have shown actually how can you measure the resistivity. So I'll briefly explain that the methodology, or let's say the knowledge, kind of like the mindset that has gone behind this. So let's say this is my sample under investigation. So I have 4 contacts, and here the assumption is that the contacts are placed at the circumference of the sample. Okay, which means that at the edges. So the idea is quite simple, that if I put it in the middle, then basically I'm losing quite a lot of area of the sample. Okay, that's why they are put at the corners. And second assumption is that the contacts have to be much smaller than the sample area, which means that they should not be too big in size. Okay. Third assumption is that, or let's say point contacts, I can say. So third assumption is that sample is uniformly thick. So I explained it already, and sample has no holes. That means it's not like discontinuous. Okay. So that is the true, and sample thickness have to be lower than the contact spacing. So this thickness have to be smaller than the separation between these. So the idea is that if the thickness is comparable or larger than that separation, then basically, since here I am mostly considering conduction that happens across the surface, that means in the plane. I mean, that assumption is valid because here it is quite thin, which means that the conduction actually happens. I mean, there are only, let's say, only very small amount of material that is present here. Okay, I mean, so it's mostly surface behavior. But if the thickness is quite large, then basically the vertical conduction will be completely ignored. Okay, so as a result, what happens is that the kind of assumption which we are taking here, that will not be completely valid for these kinds of samples. So here we assume that the sample thickness have to be lower than the contact spacing. Okay, so what do? We do a conductivity measurement, and we assume that there is no magnetic field that is present. So here we apply IBC. That means between B and C contact, we apply a current, and we measure VDA. That is the voltage will be measured between these 2 points. So applying current between these two and measuring the voltage between these two, and that will give me this quantity, that is we are defining RBCDA is equal to VDA, that is the voltage between these two, and divided by the current that I pass between these two. Now I'll do the reverse. That is IAB, I apply that is between these two and measure the voltage between these two. And then I get the resistance corresponding to that. Now, once I have this, then using this Van der Waals analysis, I can use this formula, that is rho will be equal to pi over ln2 times T times RBCDA plus RABCD divided by 2 times a factor. So this is a correction factor, that is we'll see these things. So this factor is typically 1 for a symmetric sample. However, if it is slightly asymmetric, then the value can be different from this. So here, very simplistically, what we are doing is that I have 4 arbitrary contacts. I'm taking any 2 neighboring contacts. I'm applying a current, I'm passing a current, and I'm measuring the voltage across the other 2. And I'm reversing this thing between other contacts. And that way, I can measure the value of rho between any 2 sets of contacts. And that way, I can check how the value of rho is kind of changing between different cases. Okay, so I hope this part is clear. So now the question comes. So we have discussed the methods, but how do we measure? So in the, let's say, undergraduate labs, we have like these analog meters, right? So that can help us to measure, let's say, up to microampere current. But as you know, those meters are not very much accurate, specifically when you're talking about a nano material or nanoscale systems, then the current could be very much low, like nanoampere or picoampere, like 10 to the minus 12 ampere, up to the even femtoampere, like that. So of course, those analog meters cannot be a good measurement unit because they will give us a lot of error, right? And they also have problem of, let's say, the needle sometimes gets stuck, and then there is some reversing error, then some eye estimation gives some error, etc., etc. So here, if I want to do the measurement, then I have to use some of these units. So let us look at one by one. So the first one is called as a source meter. So what is it? So here, this is something which can be used to apply a voltage and measure the current simultaneously. Okay, so typically, depending on the model which you are using, you can get up to like hundreds of volts, and you can measure current up to ampere range. Okay, so that is typically a universal system which is used for various device characterizations. Now, if I want much accurate measurement, okay, that is a 4-probe measurement. So this is typically for a 2-probe measurement is used, but you can also do a 4-probe measurement. But if I want to do a very accurate measurement, then I have to use these two. So this is a nanovoltmeter, which means that it can measure nanovolt. Okay, as simple as that, 10 to the power -9 volt. And here I have a current source. So this is a programmable current source. So this is like K36221. So here it can supply uninterrupted current, let's say up to 100 milliamp. Now here, if I use these two in combination, then I can make use of them for a 4-probe measurement, and I can do something called as a delta mode measurement, or let's say differential conductance measurement. Okay, that is DIDV. Okay, then we can use something called as a multimeter. Let's say I have a voltage source, okay, like this DC power supply. If I have, then I can use this meter to measure voltage. Let's say if it's 5.5 digit or 6.5 digit multimeter, then I can measure the voltage or current very accurately up to, let's say, at a very small current I can measure. Okay, like up to 1 or lower microamp. Okay. So now the next one is lock-in amplifier. So I have explained already what is a lock-in amplifier. So here you can see this is how the front and back panel looks like. So here basically it will show you the let's say real and imaginary part, and this is, let's say, the display where it will show you the source voltage that you are using, and you can change the frequency here. Of course, there are multiple functions you can use, and the back side you have basically ports for getting DC voltage also. So this one is also used quite a lot for these kinds of measurements. And here is an impedance analyzer. So this is for, let's say, AC measurement at high frequency. For example, if I have a dielectric material, then what I can do is that I can measure the real and imaginary part of the impedance as function of different frequency, and simultaneously I can calculate or let's say I can estimate different parameters from this thing. Okay, so these are different meters which can be used for measurement of different nanoscale systems. Okay, so now so shall we take a break now, or we'll wait?
Sure, sir. As you wish, you can take a break and
Okay.
continue after a while.
Okay. Okay.
Maybe
Okay.
after
Then
10
we'll
minutes.
start at 8:05 probably.
Sure, sir. Okay, sir.
Okay. Okay.
Thank you.
Okay. Hello. Shall I start?
Sure, sir. Welcome back to part two of today's session, sir. Please, eagerly waiting for your session.
Okay. So, please give me 1 second. Okay. So, we have seen basically how different measurements are done and basically what are the different ways and meters they can be accommodated into this. Now I'll go to some of the practical aspects. That means how different systems look like and how can we measure them. So here, for example, as we know that basically we are currently in the area of hyperscaling. That means we are scaling different systems, or let's say, uh, as a result, we are kind of like working with very small size systems. So there are three things which you need to remember here. One is that we are working with different kinds of new materials. So these are called as novel functional materials. So why they are called as functional materials? The reason is that they do offer different kinds of functionality. For example, if it's a ferroelectric material, then it has some
But
memory.
sorry to disturb you. I could not see the presentation slides,
Hold on
sir.
a second. Hold on a second. Is it not visible? I have actually shared it. Okay, hold on. Just give me a second. I think
Yes.
it's in the just again. Let me share it. Is it visible now?
Not yet, sir.
Not okay. Okay, so there is actually some strange
So
this
you,
thing
you have
down.
did stop sharing and again started it, sir?
Is it visible now? No? No?
No,
Okay.
sir. No, sir.
Okay. I stopped sharing and starting again, but it's okay. Let me just close this and just
Maybe you can do the screen share option.
is my screen visible? No.
No, sir.
Okay, let me join again. Okay. I think probably that will
Okay, sir. Okay.
okay.
Yes, sir. Now it is visible.
Is it visible? Okay, it's visible now. Okay. Okay.
Yes, visible, sir.
Okay, good. Okay, so let me go to the presentation mode and it's visible. Yeah, right?
Yes, sir. It is visible. It's good, sir.
Okay, okay, very good. Okay. Okay, so now basically what I was saying earlier that there are different materials which we are dealing with that is in the area of nanoscale systems. So they offer different kinds of functionality. For example, ferroelectric materials, they can be used for memory. Then there is phase transition materials. They also have different applications. Then we have materials like spin transfer torque and resistive switching for memory, etc. Anyway, so now what happens is that we do have these kinds of materials, and then there are different nanoelectronic devices which are made using them. For example, like this FE that means ferroelectric field effect transistors, then RERAM, that is resistive random access memory. And then there are many of these things like quantum dot qubit, etc. So using those devices, there are new computing systems that are being developed. For example, this in-memory computing, then basically neural network, quantum computing, etc. They are being developed. So you can see the multiple stages. So for example, first you design new materials, then that is being used for making devices. Those devices are getting into technology. Okay, so now here in this respect, there is basically this new kind of material which are called as two-dimensional materials, which are very much popular these days. So these are a nano material. Okay, so what is it? I'll just discuss. So as you can see, they have basically certain layered structures, and As a result of that, what happens is that they have multiple applications, for example, in photovoltaics, optoelectronics, sensor, thermoelectrics, etc. So typically, what are these materials? So let's say if I am thinking of one bulk material, there are multiple atoms which are put in a layer by layer order. Now, for certain materials, it is possible to detach one such sheet of atoms from this, and that material itself becomes a 2D or two-dimensional material. Okay, so let us take an example. So here, for example, I am taking graphite, and if I am using a simple scotch tape, then what I can do is that I can just put that tape on top of it. What it will do is that it will peel off some of the layers from top of it, and you can see that is coming here. Now, if I transfer those layers on another substrate, then it will put some of these layers here. Now, if I repeat this process few times, then I'll end up with few layers of this material on top of the substrate. So here from graphite, I can get something called as graphene layer here. Okay. Now, the question can come naturally that why these 2D materials are being formed. So the answer is that here you look at the structure here. So let's say there are certain materials, for example, let's say graphite we are talking about. So here the atomic arrangement looks something like this. So there are these layers, and here within the layer, the interatomic attraction is quite stronger compared to the outer plane attraction force. Now, as a result, what happens is that if I am applying like if I'm trying to peel up a sticky some of this with a sticky tape, then I can easily detach one or two or few layers of this particular material, and that can allow me to get a new two-dimensional form of that particular crystal. Now, up to this, you can think of, okay, so what is so special about it? Because this is the same material and it is giving me a two-dimensional form of it. The interesting part here is that the behavior of these 2D materials, let's say from graphite, we are getting graphene, that is a single layer of carbon. The behaviors of these two materials are completely different from each other. For example, a graphite is basically an insulating material. A graphene is a highly conducting material. Okay, then optical properties are also different. One is highly optical transparent, that is graphene. Graphite is not that at all. So the properties are completely different, and moreover, the 2D materials have superior properties compared to the bulk. So here, for example, from graphite, we get graphene. Similarly, from phosphorus, we can get phosphorine. So there are like a family of such materials. And since they are entirely two-dimensional, so one, that is the third dimension, is completely kind of shrinked. So that is why we call it as a two-dimensional material. So what happens here as a result of that is that the third dimension is completely gone. So that means that only we have atoms on the surface, right? So the surface to volume ratio of these materials is very, very large. And as a result, what happens is that these atoms are very much sensitive to various external excitations, and that kind of makes them more useful for designing different devices, for example, like sensors, or even like any detector, or even like transistor, etc. Okay, so here, how can we kind of fabricate, or let's say synthesize this material? So the first method I explained already, that is a mechanical exfoliation method, which means that I am taking this tape and I am kind of trying to peel up some of these layers, and I will end up with a few layers which is deposited on this substrate. Now, once this is done, then basically I can use it for making patterning and making further devices. Alternatively, I can do the same process through something called as liquid exfoliation. So here, the same, so here I don't need to peel up, like use the sticky tape, but rather I am starting with the 3D material and I am putting it inside a solvent. So what it will do is that it will disperse within the solution. Now I'll do something called as ultrasonication. So what it will do is that it will vibrate at the ultrasonic frequency, and these layers will detach from each other. Okay, so once this process is done completely, then these layers will be dispersed after ultra sonication, and I have to then filter this thing to kind of like filter out the useful layers. Okay, so now let's say these layers have been taken out. So here another useful or important step comes up, that from the material I have to make a device. How will I do that? So here is an useful instrument which is called as a thin film heterostructure design instrument. So this is a thin film deposition chamber. So here, in very simple words, what I have here is that it's a deposition chamber. That means that it's a metallic assembly, and there are multiple pumps which are connected to it. So these pumps will kind of take the air out of this chamber, and that will kind of create a very low pressure environment within it. Now, once that is done, then I have basically different materials which are kept inside these crucibles, and I can put a substrate here on top, and I will heat it up, these materials slowly. So then let's say I have material 1, then I'll heat it up, it will go and slowly deposit on top of the substrate. Okay, so that kind of helps to kind of grow one particular layer. Now here basically, suppose I have the substrate and then I grow one layer here, and then once the deposition of this layer 1 is done, then I'll go and deposit layer 2 and then layer 3. So depending on the type of structure I'm looking for, I can grow multiple layers. So basically what I'm getting here is that material to device. Okay. So now suppose I have this particular device. Let's say this is a metal insulator, metal kind of structure. So that kind of structure can be useful for a memory device. Now I want to measure the behavior or performance of this device, and for that what I have to do is that I have to do some electrical measurement, and I need to put some contacts. Okay, so there are two ways I can do the measurement. One is called as current in plane measurement, and second one is called as current out of plane measurement. So what are the differences? So in the first case, I have all the 4 contacts that are kept on the top surface here. So here you can see that if I apply, let's say if I'm measuring using a 4-probe technique, then I can apply the current here and I can measure the voltage between these two. Okay. And in the case of current out of plane geometry, I have 2 contacts here and then 2 contacts here. Now, what is the difference? So here in this case, basically, the current can be mostly flowing through the surface. Okay, depending on the resistance, that relative resistance between different layers. But here, whatever be the resistance of different layers, that does not matter. Here, I am forcing the current to flow across different layers. So depending on the type of use I have, I can use either current in plane or current out of plane measurement. Okay, so now let's say I have these things. Then here actually there is another way of making devices with a graphene layer. So here you can see this is a silicon substrate, and then on top of that this graphene layer has been transferred, and there is a another material that is called as hexagonal boron nitride. So this has a similar structure to that of graphene, which has been put underneath it. Why graphene and HBN both? Because the combination, it gives a new kind of behavior, and that's why they are used. So now these 2 layers are there, and then there is some electrical contact. So this is the titanium and gold contact here and here, and then so this is a transistor kind of geometry that have been put here. And then I'll apply, so basically I can apply voltage, I can measure the current, etc. So here actually you can see kind of a schematic diagram that as I showed you, that is a hall proof bar kind of geometry. So here I have the channel, and then I have different contacts here, etc. So now in reality, of course, this is a cartoon, like it's made up with PowerPoint probably, but you can see like how in reality they work. So these are like ACM images. So this is, let's say, the size of the 2D layer that has been put. So you can see that is like typically 20 micrometer size. And now what you do is that you take the second layer, and then so this is, let's say, graphene, this is hexagonal boron nitride. You take this layer, you transfer it on top of this. So you get the heterostructure like this. Okay, so bottom is graphene, top is HBN. And then what you do is that you put some kind of fix some contacts here. So that is kind of alignment purpose. And then you do some patterning to deposit the electrodes, and finally you end up with this kind of Hilbert geometry. So you have these electrodes on this side, this on this side, this. Okay. And typically you will have these kinds of structure on some chip like this. So you can see this is the chip. So here you have these pins on side, and you have the center. Now you have to use this probe station, as a not probe station, sorry, yeah, this bonding, wire bonding. If you remember that earlier I showed that how can you make contact from one point to the other. So here you need to make a contact, let's say from this point to somewhere here. Okay, like from here to here, here to here. Okay, so you make those contacts, and then you put this chip on top of this chip carrier. So here this is already connected. So once this chip has some pins at the bottom, so those pins will fit here, and then the electrical contacts are already kind of made here. Now this will fit inside your let's say cryostat or whatever measurement equipment you have, and you can do the measurement. So here is another kind of chuck which you can use. For example, you can put the sample here, and you can make the, for example, like this one, you can put it here in the middle, and you can make the contacts from here to here, here, etc., depending on what you are doing. Okay, so that's how basically from device to contacts that you do. Now, very simplistically, if I want to do a measurement, then what I will do is that I can make use of something called as a cryogenic probe station. So this is a very simple and way of measuring IV of these kinds of devices. So let us look at how does the structure looks like. So here basically we have a stage, and these are the legs. So this is the support. And now what we have here is that we have basically 4 arms. So these are called as controllable arms. So they can be like adjusted. So you can either push it, pull it, etc. And they are basically electrical contacts. So there are electrical contacts on this side which touches the sample, and there are these electrical ports, like you can see these coaxial connectors. So they will be connected through from here to some electrical measurement equipments. And now there we have a glass window, and there is a microscope. So this is an optical or traveling microscope. So this kind of gives us a zoomed image of what is happening inside. And usually this is connected to a computer. And this is an adjustable kind of stage. Okay. Now there are 2 additional parts which we have. So okay, first of all is that it has 4 controllable arms, which means that 4 contacts we can get, but it's not only 4, you can actually have more than that. So you can get a back gate, or you can have another also. Now this system is usually connected to a pumping line. Okay, so here you can see these big valves, etc. So usually you can connect it to a pumping line, and that will kind of take the gas out of this chamber, and which means that you will measure the sample under the vacuum condition. And alternatively, if you want to do measurement under certain conditions, let's say under the influence of a gas atmosphere or etc., then you can also do it. So all you have to do is that you pump it out first, then you put that particular gas through this port, and you are kind of done. And another option which it has is that it has a cryoport. So cryoport means that you can put some cryogenic fluid like liquid nitrogen or liquid helium, and that will kind of help you to cool the stage, so you can do a temperature dependent measurement. Okay, and you can control the temperature through this temperature controller. Now if I look at the inside view, so this chamber inside view, if I look at, then here you can see this is kind of quite shiny, so it has a radiation shield. And then the device under test, that is kind of kept here, and there are electrical contacts. So they are like different pins. Okay, they're like tungsten tips which are used here. So they kind of come up and then touch it. So and inside you can see there are basically different stages, etc. So here once you put the sample, it locks. So you can basically fix it here, and then you kind of let's say close the lid, and you can do the rest of the adjustment through the microscope, and by kind of like looking at from the computer screen. Okay, by adjusting different things, etc. Okay, so now let's say you have made all the things. So you have the sample inside, you have made the contacts, etc. Now you want to do the measurement. So what you will have to do is that these electrical ports have to be connected to some unit. So as I said earlier, that you can use some source meter or some multimeter, power supply, etc. So you connect it. Now, since these are programmable, so you don't need to physically change the voltage or current here. You can actually control it through a computer. So here you use some sort of this GPIB, or let's say some interface bus cable. And so you can see this back end will be connected to a computer screen. And here you need some program like a LabVIEW or something similar, which will kind of communicate between the computer to the instrument, and that instrument will perform the measurement and collect the data. So here, for example, this is a simple IV script which is measured with LabVIEW. So here you can see that basically, so what you do is that you have these parameters which you put here. That like what is the initial voltage, final voltage, step size, okay, number of cycles, etc. And here you can see that this measurement is being done. So here this is like an IV characteristics of a field effect transistor. Here you can see this kind of for different gate voltages, you get different kinds of these graphs. So that measurement can be done. So here you have to do a little bit of scripting here, but that is not too difficult. All you have to do is that you have to know how to communicate, and like these are quite standard and standalone kind of protocols, and they can be used. Okay, so now this is the most simplest way of measuring. Alternatively, what you can do is that if you do not want to do that much manual exercise, then you can use something called as a semiconductor parameter analyzer. Now, of course, this is a slightly expensive system. So here you can see this is something which looks like this. So this is like a touchscreen kind of unit. So here, this one works on behalf of the computer and the meter itself. Okay, so here you don't need any LabVIEW or any interface cable, etc. You just directly connect this thing to the chamber, this probe station. And here you can basically write down, I mean, here programs are already given. You have to just slightly modify them, and that you can use to do the measurements. Okay, so this is also another way of doing this thing. Now, let's say, suppose you have done the measurement. Now I'll give you a couple of examples of how different nanoscale systems can be characterized. For example, let's say I talked about graphene. Now, graphene is very good as a sensor. So what is a sensor? So typically a sensor means that is able to sense something. For example, we know in our human body, we have our like ear, nose, and then our let's say eye, etc. So eye is like an optical sensor. Ear is like an audible sensor, sound sensor. Like similarly, we have multiple sensors like in our mobile phone, in our car, etc. Even like shopping malls, you have seen like the door opens and close, etc. Okay, even like simply if you have like a thermometer, that is also a sensor. Okay, now graphene as a material can work as a very good sensor. So the reason why why it works as a good sensor, I said already that it has very high surface to volume ratio. So it is sensitive. Now the sensitivity of graphene for sensing can reach up to, let's say, very high limit. For example, like parts per billion, or parts, like you can see like once in a billion, like that much limit. So like one atom in 1 billion atoms that it can resolve. Okay, so it's a very high level of detection sensitivity it can give you. So let us look at how, let's say, suppose you have designed a device which is a sensor and you want to characterize with this kind of probe station. Okay, then so you have made the device, you connected, measured. Now how will you do the measurement? So here, let's say the first what you do is that you measure the IV curve in the as fabricated configuration. That means you do not do any changes. Okay. Now suppose this is a gas sensor or it's a light sensor, anything. So what you do is that you do a fast exposure, which means that suppose it's a carbon dioxide sensor. So you just suppose the first measurement was done under vacuum, then the first exposure means that you are just passing some carbon dioxide gas, some controlled amount, and then you measure the same IV curve again. Then you take the gas out. Now you do a second exposure, you measure. So you can see like how do the IV curve varies between different cases. Okay, that will give you an idea that what is the sensitivity. That means what is the difference in value of current that is happening in different cases. Now, here you can do a dynamic measurement also. For example, suppose you can measure the sensitivity. That is basically, let's say here, this is defined in terms of the resistance between the exposed and unexposed condition. And it is measured as a function of time. So let's say we're starting from 0 time, 0 second, and then we do measure this sensitivity, nothing. Then we start entering some gas. So slowly you see if it is sensitive to the gas molecule, the sensitivity will increase very rapidly. So this is, let's say, 5 ppm, that is parts per million. And then within very small amount of time, it will saturate. So once it saturates, then you stop the flow. So what it is happening is that it will fall down. It will fall down. Then it is completely taken off the gas molecule. So it is again reaching this bottom level. Now you pass again the gas, but at a lower concentration than this one. So now it is 1 ppm. So here also it will see as soon as the gas enters, it will kind of increase, and then again once it reaches this saturation, then it will you stop it, then it will come down, and you can subsequently do it at different conditions. So that way you can get an idea of how the sensitivity of this system works. Okay. Now here there are two important parameters which you can define. So here you can see in the inset there are two time scales that has been defined. For example, when the gas is on, then how fast the sensitivity reaches saturation, that is called as the on time scale. Okay, and here also on the off state, how fast it reaches from this top to bottom, that scale, time scale, is called as the off scale. So you can simply think of like an RC circuit. Okay, there is some time scale, like time constant you define, like the time it takes to charge, the capacitor takes to charge 1 by E of its maximum value. So here also something similar you are defining here. Now the slower these time scales, the better is in terms of sensitivity. That means the sensor responds very fast. Okay, so here this is like an on response, off response, and depending on time scale, you can actually kind of like find whether it is good for rapid sensing or let's say slow sensing. For example, this time scale, whether they are comparable or not, etc. Okay. Now here you can also measure the sensitivity in terms of concentration as function of temperature, and here you can see how do they behave. For example, here in this case, this sensitivity increases with concentration, which means that if the behavior is linear, that is quite kind of good. Okay. And with temperature also, you can see if you are getting reproducible behavior or similar kind of trend or something that is not reproducible. Okay, different from each other. Okay, now here also you can see, so here in the first panel I have talked about gas sensing, but you can do it with another species. For example, in the bottom panel, this is with ethanol, and you can see for different concentration of ethanol, they have done the measurement, and here you can see basically this cusp is kind of a different height. So that is something which is expected, and you can define the sensitivity at different temperatures, and you can see that sensitivity also changes with temperature. So there are different factors which you, of course, I mean, you can collect the data through electrical characterization, but you have to do the analysis in order to kind of find out whether this is a good thing or a bad thing, etc. Okay, and now you can actually see if I do a direct resistance measurement with time. So here, for example, this is a graphene oxide, and that is measured in the presence of NO2. That means nitrogen dioxide. And here you can see that this is 20 parts per billion, and they have increased like 40, 100, 200, up to 10 ppm. And with the increase of this, how do the sensitivity changes? So you can see this kind of these oscillations, the amplitude changes. Now, this kind of behavior, or like these measurements, can also be very useful for designing biosensors also. For example, here this is like some okay, this is not biosensor, but this one is biosensor. But here actually this is some mercury ions which have been put here, and you can see like it is even sensitive up to 0.1 ppb. So you can imagine like how sensitive these devices or these nano electronic devices could be. So here it can resolve the current up to this level. And here this is a biosensor. So this is some DNA molecule which has been put between on the channel area. And the threshold voltage here also you can see like up to 10 to the power minus 14 mole. So basically as soon as the DNA molecule comes up here, there is a threshold voltage. So here like this voltage, it changes. Okay, and the difference of the threshold voltage is measured. So even at 10 to the power minus 14 mole, you can see that there is a difference. So here you can see there are different conditions, like different types of DNA which have been put, like complementary DNA and I think non-complementary. So depend, like for different species, you see different kind of response, but it is kind of quite linear. So which is very good property as a sensor. So we have already, I hope we understood now that how transport measurements can be useful for understanding different kinds of, let's say, nano material property. Okay. So here I have only explained the sensing property here so far. Okay, so now I will talk about another nano, let's say, material or nano electronic systems or nanoscale system. Okay, so here we'll talk about something called as magnetoresistance. So what is it? So we learned about resistance, but for some material, what happens is that the resistance of the material, it changes in the presence of a magnetic field. And the difference between these two is called as basically magnetic resistance. Okay. So here we can artificially create some structures. So these are thin film structures, and these structures can actually be used as memory. So basically, we are kind of controlling the magnetoresistance, and this is being used as memory, or let's say as a switch. Okay, so here I will explain how do these things happen. So here basically these are thin films. So they're like, as I said, like you take a silicon substrate, you grow one particular material. Let's say this is iron. Okay, this is copper, etc. So you grow a very thin layer of iron, typically let's say 100 angstrom or something like that, or 200 angstrom. Okay, and then you grow a non-magnetic layer that is like again very small thickness layer. So this is like nanoscale systems. So what happens is that in this particular case, this is a tri-layered system. So we have two ferromagnets. So we know what is a ferromagnet. That means a material which has a non-zero magnetization even in the absence of a magnetic field. Okay, so here let's say I have an iron layer which I have grown, and then this is also an iron layer, and in between I have a non-magnetic, that is a copper layer. Now I can basically create a relative magnetic state between these two layers. For example, I can create a parallel or anti-parallel combination of the magnetic state between these two. Let's say it is in the parallel state. That means two ferromagnets are magnetically aligned in the same direction. Now, if I want to pass a current from left to right, then since it is magnetic, so here the electrons which will flow, they will also be spin polarized. What do I mean by spin polarized? You know, like electrons, they have basically, they can carry two spin types. One is spin half, they're spin half particles. So either the spin can be up or spin can be down. So now let's say if the spin is up, then what will happen is that since the spin is up, so it will see that this is also up, and here also this is up. So it will face very little resistance, and it will see similar types of kind of environment between from left to right. So it will easily pass. Okay, so these up electrons will easily pass. They will not face much resistance. But if I think of a down electron, then this down electron will see that, okay, this layer is magnetized in the opposite direction. So it will not be very easy for me to travel. So it will face a lot of scattering. So you can simply think of it like this way, like you have a very busy street or road, huge traffic, and you're trying to run. What will happen is that any way you try to run, you will hit somebody, right? So you will face some resistance. So it means that from point A to point B, you cannot travel without scattering. So here also same thing happens. So the down spin cannot travel that much, which means that the number of down electrons which will come here will be very little compared to the number of up electrons. Okay. However, if I look at the anti-parallel configuration, then here, let's say if it's a down electron, then it will face quite a lot of resistance here. But if somehow it survives, then it will face a slightly smooth path here. It will come here. If it's an up electron, it will get through smoothly here, but it will face a lot of scattering here. So here, no matter what the spin type, it is up or down, both of them will face a lot of resistance, which means that the number of electrons which will finally arrive on the right hand side will be fewer in number compared to this case. So here only down spins are electrons are low, but up spins are high in number. So for the first case, that is in the parallel case, the current will be higher compared to this case, which means that here current is higher. That means the overall resistance of the structure will be lower. And here the overall resistance of this structure is higher. Now, what is so big about it? So just think of this. I have created a simple tri-layer structure, and by just way of controlling the magnetic state, that means I'm just creating a parallel and anti-parallel configuration. I can actually create two different resistance states. Okay, one is high and other is low. So I can simply use it as an on and off state. Okay, so it's like a valve that I am allowing something to flow and I am not allowing. Okay, so these kinds of structures are called as spin valve structures. Okay, so now there is something remarkable which has come up. For example, the first measurement which have been done on these kinds of systems was on iron and chromium, and you can see that if I use that iron and chromium stack, so here basically there is iron is 30 angstrom thick, and then chromium is, so chromium is basically this non-magnetic layer that is 18 angstrom thick, and here I have used like 30 repeat of this thing, then I have iron 30, chromium 12, so the thickness of the chromium is reducing. And what happens is that if I measure the resistance, let's say as function of magnetic field, then I see that if it is high magnetic field, okay, then the resistance is quite low. But as soon as I reduce the field, then the resistance becomes very high, and then it again shows the same kind of behavior on the positive field direction. So here simply you can see like when it is in the zero magnetic field, that means in the antiparallel state, and when it is in the, let's say, high magnetic field region, then it is the kind of low magnetic resistance. Okay, so here simply I can define something called as a magnetoresistance, that is rho antiparallel, or let's say R antiparallel minus R parallel divided by RAP. Okay, so here that is the ratio between this resistance and that level. Okay, so here smaller the thickness of the special layer, higher will be the resistance ratio between these two levels. So this is called as giant magnetoresistance effect. So by way of simply changing the magnetic field, I am creating a giant difference between the resistance at different conditions. So for this discovery, actually, these two scientists got Nobel Prize in physics in the year 2007. So his name is Peter Grunberg, and this is Professor Albert Fart. Now, this has huge technological applications. Okay, so here let's say there are some typical systems which have been taken. For example, if it's an iron chromium, then you can see the ratio is like 100%. Then cobalt copper also, this is quite large. And then for different cases, these numbers could vary between like 10 to 100, something like that. Okay, so now if I look at, so basically this particular kind of resistance, magnetoresistance structures can also be created if I in a different way. That means here earlier we have used a metallic layer, that means copper or chromium, but I can simply use a non-magnetic layer to separate between these two ferromagnetic layers. So the geometry is quite same, but the mechanism in which the current travels will be slightly different. Okay, so here what happens is that it is an insulating layer, let's say an oxide layer like magnesium oxide or aluminum oxide, something like that. So here basically the spins will kind of have to tunnel from here to here. Okay, so if let's say the red electrons, let's say there are up electrons, they are trying to flow from here to here, then if they are in the parallel state, then it is easier for it to travel here because it will face more less resistance, or let's say there will be more available states for it compared to the other one. So here basically the resistance in the parallel case will be quite small in a similar argument, basically because here these red electrons will flow in larger numbers compared to the blue electrons. But in the antiparallel case, both the red and blue electrons will face scattering here, so they will not be able to kind of give a large amount of current. So that means the resistance in the antiparallel case will be higher here also and lower here also. So these kinds of structure is called as a tunneling magnetoresistance structures because the current tunnels from one side to the other. So now the reason why this giant magnetoresistance and tunnel magnetoresistance came after giant magnetoresistance is that the resistance ratio that we are getting here we are getting something like 100, right? Here this number can go much higher, which means that the sensitivity will be much higher. Okay, so now I'll show the applications in the next slide. Now here, suppose I have to make a parallel and anti-parallel configuration between these two layers if I want to make use of them. Now that is slightly tricky sometimes because if certain cases can appear that both layers are switching at the same time. Okay, so here another arrangement can be done. That means let's say if I am using something called as an exchange bias arrangement. So here basically I'm using an antiferromagnetic layer to pin down one ferromagnetic layer. So that way, basically, let's say this bottom layer will have only one particular magnetic orientation. It is pinned. It cannot be changed. So I only need to flip the magnetic orientation of the top layer. Okay, that is easier. So that way, basically, I can get easier control. So here you can see that how different types of structures in reality looks like. For example, there is an silicon dioxide layer. Then I have a bottom electrode. So this is like silver or gold. Then I have an antiferromagnet. Then I have a pinned ferromagnet. Then I have the free, like the kind of like separator. And then I have the free ferromagnet and then top lead. So basically, I measure the current between these two blue layers. Okay. So that way I can basically there are different material combinations which are used to do these things. Now here you can see some result that basically if I make use of this, then I can actually create this logic state. For example, this is the 1 and 0 kind of state. Okay, and here you can see how do the this magnetoresistance ratio has evolved with time. So this is actually stopped at 2005 because soon after that this material actually this technology got commercialized. So here you can see it started with like 0.50, then slowly it has gone up above 400 and now it is in thousands. Okay, so what is the application of this thing? So basically I'm using a simple tri-layer structure to create parallel and anti-parallel state, and that can be used as a switch, as a memory. So even until few years back, like all the computer hard disks that we are up here using, okay, they are kind of the read heads or the memories, they are kind of using this particular technology. So what happened is that here, this is like, let's say the this tunnel junction. So they are called as this MRAM, that is the magnetic random access memory. Okay, why random access memory? There you can see that they I have some memory effect. Okay, so here there are multiples of these structures which are used, and there is some common electrodes which are connected in the bottom and top. So here basically I can create, like by aligning them either parallel and anti-parallel, I can create 0 or 1 state, and there are kind of like bit lines and word lines. So I can use them for like let's say read head of the hard disk type, for example, like reading information, or even like memory. Okay, for example, simple memory, I can use it. So like IBM first patented this technology and they have used quite a lot. I mean, after this. Okay. So this is again another system where you can see that where these transport measurements in a nanoscale system gave remarkable result, and that has made huge technological development. So by the way, so nowadays, whatever memory that we are using, this flash storage, I already showed in some of the slides there, like this resistive random access memory, those flash storage are actually being used in some of our mobile devices or even like our hard disks already. Okay, so now if I want to do these kinds of measurements, what I have to do is that I need something like this. So I need an electromagnet. Okay, so this is like a lab-based electromagnet. And if I want to do a slightly complicated measurement, then I need a magnet, which is slightly higher strength. And then I can place the material here, and then I can do the measurement with this. Now, very simply, what happens is that these big electromagnets, they require quite a lot of cooling and a big power supply. So you have to kind of take care of these things because we are passing a current between this, and this current could be quite high. So there could be a large amount of heating. So here you can see basically the cooling is required, and then you need a bipolar power supply, which means that you are switching the polarity of power supply between these two. And you can also use an AC source to kind of like if I want to kind of create an AC magnetic field. And further options are possible. If one wants to use a cryostat to do temperature dependent measurement, then you can connect it to a probe station. Okay, for example, these things. Then you can use an optical port. Then you can make use of sample rotation. So there are multiple things you can do. But anyway, finally, you are measuring transport property. Okay, IV basically in different conditions. Okay, so now there are various fancy measurement systems. Here, this is called as a basically quantum design physical property measurement system. And then here we have like how do the like measurement. This is the transfer or sample stick, how it looks like. So here actually you can see like this is the part where you store the sample. Okay, and so these are quite fancy actually. So if you want, I can explain. So like, let's say this is the part where you have to put the sample, then you have to connect the pins. Now there is a stepper motor, which is kind of going to rotate it, and then you can also create a local magnetic field. So there are different things which you can do, I mean, depending on the type of use which you have. Okay, so that way basically you can do different kind of magnetic resistance measurement. For example, like I want to do measurement like a, like this hallmark kind of geometry. Either I want to measure in the off diagonal direction or perpendicular to these different directions I can use. So similarly, I can use magnetic field in different direction. Okay, like a vector magnetic field I can create. Okay. And then some of these measurements are also quite useful for something called as this quantum technology. So you have probably heard of like this year the Nobel Prize in Physics was awarded for this quantum entanglement or quantum technology. So the idea is that we are using quantum mechanical protocols to transfer data or let's say do the computation. Now, usually since these quantum mechanical signals are, let's say these measurements are very weak signals, so we need to do the measurements at very low temperature. So typically like let's say millikelvin temperature or something. So we need to create those temperatures, and that is usually done with something called as the dilution refrigerator. So there are multiple stages of cooling which you can see, and that is kind of being used to create low temperature, and then you do the measurement, and kind of that is kind of useful to explore different properties. Okay, and here are actually some results which actually you might find interesting. For example, there is like they're like pioneering works like this discovery of Majorana fermions. So here you can see like very sensitive transport measurements people have done, like this DIDV. There's a differential conductance measurements one has done. You can see the range like -100 to 100 microvolt, and here actually they can resolve this kind of conductance peak at low temperature. So these are like very like new discoveries. And then here you can see like quantum Hall effect for graphene. So here you can see that basically this this conductivity becomes quantized, like it becomes in terms of like uh, mm, like h over e square, that units like 0 1 2. So they are used at like these things can be used as resistance standards. Okay, so you need very sensitive kind of like transport measurements to do those things. Okay, and then also here something like this magic angle graphene. So people have observed superconductivity here in this sample. So what happens is that there are like 2 layers of graphene that have been taken, and then what people have done is that they have rotated it by a very small angle, and what they saw is that like graphene itself has some resistance, right? Like I said, graphite is insulator, graphene is conducting, but if you take 2 layers of graphene and then rotate them by a very small angle, let's say 1.1 degree, then the resistance completely disappears at a very low temperature. So it becomes superconducting. So you can imagine how material property at nanoscale can change. Like the same material is becoming completely resistance less. And so again, for these kinds of measurements, you need to measure very small amount of current. And here people have tried to explore like, I mean, through different kinds of measurements, like how off diagonal voltages behave, and how kind of like what sort of current voltage dependence do they have, etc. So I mean, these are some examples of these nanoscale systems, and how these electrical characterizations can be very much useful. So they're like integral part of this. So simply starting from a lab scale, we can go up to these fancy measurements, but it's not always that you need very expensive equipments. In some cases, the lab-based equipments can also be modified, or let's say you have to kind of fix some measurement protocol to measure, let's say, very sensitive kind of current. So you have to get rid of the noise, and then you have to make sure that you are measuring the sample contribution. So if you're careful, you can do quite a lot of useful information. So the transport measurements itself are very much useful for probing these nanoscale systems. Okay, so I of course could not cover most of the things. So with this, I have come to the end of the presentation. So there are other systems, for example, like I have not discussed these energy materials, like thermoelectric materials, like where basically this Seebeck coefficient or thermal conductivity, they are quite useful, because these thermoelectric materials, they can actually harvest energy. So they can convert the heat energy into electricity. So for that, the electrical conductivity and thermal conductivity both are important, and they can be measured. So these are like some of the things which are quite useful again also. So with this, I would like to finish here. And if you have any question, you can ask me. Thank you all.
Yes, sir. Thank you very much, sir. I request the participants to interact with the resource person Soumya Jyoti, sir. So if you have any questions regarding this transport characteristics, so how it is very much useful, particularly in for developing the electronic products. So miniaturization is only possible because of the concept of this nanoscale systems and particularly for electronic devices in power electronics, all these kind of systems, electrical characterization of devices to determine the resistivity, carrier concentration. So all these things discussed by sir, and so many things about the novel computing systems of nanoelectronic materials or nano functional materials discussed by sir about the cryogenic probe stations and parameter analyzers of this. And another important concept on magnetoresistance and nanomagnetism and spintronics, very well explained by you, sir. I think there might be a lot of questions to the participants, but some may be
If you have
hesitating.
any question, you can type it also here in the chat box.
I will give you your email ID also, sir, with your
You give
permission.
me no, I'm saying right now in the chat box also, if anyone is interested to, I mean, you can also type your question if you want. If you are. So to the participants, I'm saying, if you have any question, you can also type it in the chat box. Anyone has any question?
Please, you can interact through chat or to direct interaction anyway.
Right. So I'm switching on my camera. Probably that will help. Okay. Yes. Now you can ask me also. You can see my face now.
Hello.
Hello. Yes.
Sir, I think you have done characterization for magnetic field, right?
Yes.
If what will happen if both magnetic field and electric field strikes the surface of the body?
You're saying magnetic and electric fields are simultaneously applied.
Yes, yes, yes.
Okay. So what will happen? Is that the question?
Yes, sir. Yes, sir. Yes, sir.
So I mean, it depends on like what type of material you're dealing with. If the material is a magnetic material, okay, then of course it will go to some magnetic state. Let's say if it's a ferromagnetic material, and if you're applying a magnetic field, then it will go to the saturation state. Okay, which means that it will reach a high magnetization. Okay, right. Now, if you are applying an electric field, so I am believing that you are going to measure a current after this, right? That means you are applying a voltage to measure a current. Is it that?
So actually, the thing is, for example, if we take the stealth application.
Which application?
Hello?
Yes,
The
yes.
stealth application, like the bodies are subjected to radar signals.
Right. Okay.
Where the memory is subjected to both electric field and magnetic field simultaneously.
Right. Yes.
So there should be characterization should be done for both magnetic field and electric field.
You can do. That's what I'm saying. So let's say you, I mean, see the signal that you will get. I mean, you cannot. I mean, you of course there is a way, but like usually you don't separate them, right?
Yes,
So
yes.
you apply whatever you want to apply. I mean, experimentally you can apply both the let's say electric and magnetic field to a material, or let's say to a system at the same time. That is not a problem at all. Okay, you can do this thing.
Okay. Okay.
And you can also measure, like let's say here I talked about electrical property, but you can also measure the optical property also. For example, like if you want to measure like absorption behavior, or let's say you can measure, I don't know, like a Raman signal, you can measure, you can do that measurements also. Okay.
Okay, sir. Okay, sir. Actually, the main objective is where absorption is the main property only. They need. That means if the radar signal is transmitted to some body surface,
Yes.
the entire signal should be absorbed by the body.
Yes, I mean for that particular case, it is, yes. I mean, I don't know much details about that particular application, but I mean, yeah, I mean, it can be absorbed. Yes.
Yeah, because you have mentioned the characterization for magnetic field, that's why I'm asking. If both
So
magnetic and electric fields are same.
yes.
Yes,
See,
sir.
for example, this last part where I talked about, see, I am applying a magnetic field, but finally I'm measuring a current, right?
Yes, sir.
So if I am measuring a current, that means I have to apply an electric field.
Okay.
So without an electric field, I cannot measure current, right? So when I'm talking about like resistance is higher in the anti-parallel configuration or resistance is lower in the parallel configuration, if I want to measure resistance, I need to have some electric field applied. So the electric field is there, of course.
Okay.
Yes.
Okay, sir.
Yes. Any other question from anyone?
Any other questions from the participants? I think if there are no more questions, I think it is very elaborate explanation. So it's well understood by everybody, all the participants. I would like to thank you, sir, from on behalf of the Department of Mechanical Engineering, JNTU Gurujada Vijayanagaram University, College of Engineering Vijayanagaram, and all the participants who attended today for this Atal FDP program. So this is a wonderful session, and thank you very much, sir, for sharing your valuable expertise to all our participants today. Thank you very much, sir.
Thank you.
Thank you for being with us.
Okay, thank you. Okay, bye.
Bye, sir. Bye. Thank you.